And let me get this video. Great picture, but okay, today we have mature Myeong. I'm pronouncing that right. So, good enough. He's visiting Padua, and he's come down to give his talk. He got his PhD in Cambridge at IOA, and then was a postdoc in the CFA in Harvard, and now has come back with a Weaver Home Fellowship to Cambridge again. His work is in large data sets like Gaia for doing dynamics and structure of the Milky Way. That's what he's going to tell us about today. Thank you.
Thank you. Hello, buongiorno. Thank you very much for your time today, and thank you for the opportunity for me to give a talk at Bologna. It's lovely to be here. My name is Myeong, and today I'd like to talk about some of the research and a brief overview of the galactic archaeology that have made use of a number of large-scale surveys such as Gaia, APOGEE, GALAH, and others. Now, one of the main goals in galactic archaeology is to understand the formation and evolutionary history of the galaxy, which can help us to learn about and also to test the governing physics in the galactic scale. So Milky Way as a test set actually provides us many advantages in this sense that first of all, there are many traces that we can make use of for the science cases. And the necessary information, such as kinematics or chemistry, can be obtained in the size and the quantity, in the quality that is quite difficult to achieve for the other external galaxies. So the stars, like clusters, like stellar streams, are all great traces, which actually spans across the galaxy, even to some very large galactic radii. And we can trace the galaxy's components, their properties, like their mass and morphology, and even their origin. And we can trace the mass distribution of both normal and dark matter, and even look for the sign of some dark matter subhalos. Now, the one thing to note here is that whether is our Milky Way a typical galaxy or not, the mass-wise, it probably isn't really a rare one, as we see like many galaxies with comparable mass and the similar morphological type. We see like similar galactic components such as bulge, from other galaxies as well. On the other hand, it probably is atypical with regards to its assembly history. It seems the Milky Way had a major galactic merger event about 10 Gaia years ago, and had most of its components arranged, sorted by then, and then have been having a relatively quiet time since then. So it is, of course, important to know if our galaxy is a general one or not so general case across the universe, but this actually becomes less of an issue once we kind of obtain a detailed understanding on the Milky Way's assembly history, and also that if we can actually trace its assembly, understand its assembly mechanism in details. So now we know that our Milky Way consists of the bulge and the bar at the center, and the disk and the spiral arms. And surrounding them, there is a halo, which may look rather elusive. The stellar halo consists of mostly old and metal poor stars, and it is very sparse in density. And it is a good, and the good portion of the halo actually exists in form of halo globular clusters. And the halo structures is also almost entirely supported by the velocity dispersion. Now, the Milky Way's halo actually provides a particularly interesting arena for our study in case of the galactic assembly. The lambda CDM predicts a large galaxy such as our galaxy has been formed by the hierarchical accretion of merger of numerous proto or smaller dwarf galaxies. And during this process, the debris would form the stellar halo. So as the halo has mainly been formed from this past hierarchical accretion, the halo structure or substructure are the direct reflection of this assembly history. Now, the halo substructures, such as stellar stream, they are excellent tracers for dark matter halo as well, because it is it's a substructure with still having some physical coherence in the configuration space, and they usually are on very eccentric orbit, meaning they orbit across a very wide range of galactic radii. So they are very good tracers for galaxies' mass distribution, and in addition, they could be a good probe to look for the potential dark matter subhalo, which can actually perturb some stellar streams. Now, while the galactic halo actually holds very many clues for understanding the galactic evolution, the Milky Way halo is very sparse in density and making it very challenging to obtain sufficient data until rather recently. So before the Gaia, there are only about 100-ish halo stars within 1 kiloparsec from the sun that we can actually obtain the full 6-dimensional phase space information. Or in most cases, we are severely limited to the 2 to 3-dimensional information, which is usually sky position plus some line of sight velocities. So a series of recent data release from Gaia actually changed the situation dramatically, as it improved more. Now it's providing more than 1.5 billion stars across the whole sky, and also comes with the 5-dimensional phase space information, which also extends to, say, 10 kiloparsec from the sun. So it actually covers the very sufficient volume beyond the disk across the galaxy. So combined with other existing spectroscopic survey, such as APOGEE, GALAH, so we can construct a very good volume of data that consists of the complete 6-dimensional phase space information, which is positions and velocities, plus various chemical abundances for individual stars. So this is, I guess many of you already know Gaia like very, very well. So this is a very rough sketch of pre and post Gaia time stellar sample coverage across the Milky Way, and so we can see like such a dramatic change that Gaia has provided to us. Here is a Gaia satellite getting ready for launch, and you can see this space laboratory is actually quite big in size. And it is now orbiting in L2 point now, which the JWST recently joined. So this is a color map, probably seen it many times, from Gaia DR3, where all the stars with the color information, which is BP and RP, are plotted here. And we can clearly see like some of the main structures, like a bulge, disk, and also the dusting, and a number of globular clusters are also visible like as dots here and there. And then we can see very clearly our Magellan clouds. Now there are some. These are some other demonstrations for Gaia stars. With the top left showing the radial velocity, bottom left the radial velocity plus the proper motion vectors, and some interstellar dustings and the metallicity, which is a additional information that came along with the DR3. Now Gaia itself is a remarkable data set indeed, but the combination with other survey data, especially with spectroscopic data, makes even greater synergies. These have been, there has been a number of wide sky spectroscopic surveys, such as APOGEE, NAMOS, and GALAH, which provides radial velocities and various chemical information as well. Now, the Gaia's astrometry made it possible for us to attempt a full chemical and also full kinematical analysis for the stars across the Milky Way. Now, having a complete phase space information, which is positions and velocity information for individual stars, also gives us a very big advantage that we can actually try to do more than simply looking at the current location or current motion of the stars. We can actually have more fundamental approach that we can study their true dynamics or get the integrals of motions information. The action angle variables is one of the example, which provides a very intuitive characterization of the orbit of individual stars. So it also reduced the 6-dimensional phase space parameter space to a 3-dimensional one. It is also adiabatic invariant, so meaning it can actually. So it allows us to have a glimpse of the past state of the current day properties from the current day properties. So it is like a living fossil, very suitable for the study of galactic archaeology. So altogether, we can finally do a full chemodynamical analysis for our galaxies, even for the galactic halo, which always has been a challenge. A little more detail with the action angles. So the action provides a very good and simple characterization of an orbit. And now the Milky Way structure can be viewed as a collection of orbit of Milky Way stars. So the overall structure is a sum of individual orbits. In this perspective, the action variable is like providing a code map for our galaxy structure. This analysis, especially in large scale data, only have become available in rather recent years, thanks to the development of various numerical methods for fast calculation or estimation of actions with realistic galaxy potential, which doesn't have a analytic solution. The more precise way would be doing a full orbital integration for individual stars, but this is relatively computationally expensive. But now there are many methods for fast approximation, which is consistent and sufficient enough even for the large data set. Now, another main approach for investigating our galaxies, of course, is from the chemistry of individual stars or populations. Stars with common or similar origin naturally have comparable energy and chemical compositions, and these chemical abundances can reflect its formation environment. So there are also various elements tracing different nucleosynthesis, such as the alpha elements from the alpha process, or neutron capture elements such as S process or R process. So there has been various attempts on the large-scale chemical tagging or mapping for the Milky Way stars, such as GALAH. So for more details, GALAH DR3 has a very nice chemical tagging paper. The chemical abundances of the star depends on the main interstellar medium polluter from its previous generation. So for example, the nucleosynthesis in the supernova type 2 and the supernova type 1A is very different. They contribute to different kinds of and ratio of elements at the end of its life, their life. They also have a significantly different delay time from the star formation, meaning that there are different periods that each type of supernovae act as the dominant ISM polluter. And the transition between such dominance such dominance causes noticeable change in the abundances ratios. Now, for example, the supernova type 2 are from the higher mass stars, which are short-lived. So they occur from earlier time in the galaxy. So, and during this time, supernova type 2 yields are the main source of the pollution, which is reflected, of course, in the next generation stars from those gas. Now, the Fe/h, the metallicity in the gas, normally increases as the time goes by. So while this rate is related to these star formation ratio, primarily linked to the host galaxy's mass. But as the supernova type 1A eventually kicks in, since they are the main channel of iron peak element production, the alpha/Fe ratio in the ISM will drop significantly, which is again reflected in the abundances of the following generation stars. So this delay time is quite universal. So you can see this as a race between how fast the Fe/h is getting increased before the supernova type 1A kick in, and which starts dropping the alpha/Fe ratio, for example. And this is related to the star formation ratio, which again is normally proportional to the host galaxy's mass. So there are very noticeable difference between the Milky Way stars and the stars from the smaller dwarf galaxies. And of course, due to this significant difference in their mass and the correlated star formation rate and so forth. So simply speaking, for the heavier mass galaxies, you kind of expect to see this kind of transition happening in the higher metallicity. So another example is also element, such as aluminium or sodium, that similarly to the case of the alpha/Fe, the rate of aluminum enrichment drops on the it depends on the star formation rate and the degree of self-enrichment. And of course, this ratio changes when the supernova type 1A kicks in, which is the main source of iron peak element. And the degree of aluminum enrichment is a very good indicator for the birthplace of the stars, as it can tell us about their host. Now let's have a quick look on some of the results from the Gaia. Here are so here we are examining the halo stars in action and energy dimensions in two separate subsets, representing the metal-rich halo and the metal-poor halo. So relatively younger and the relatively older components of the Milky Way's halo. And we can kind of see that distribution looks quite different, even from a very simple metallistic cut. And so here we are showing like two actions, azimuthal actions and radial actions. On the x-axis and the y-axis, there's the orbital energy of individual stars. So the left two is the relatively younger stars with the higher metallicity, and the right is the relatively older ones with the relatively lower metallicity. Now the azimuthal action here, J5 is LZ in this case, and so the negative J5 indicates the stars is orbiting retrograde side, so negative values, and the positive J5 indicates the prograde orbit, which means the star is orbiting in the direction of the galactic rotation. For the stars at the same energy level, closer to zero means it doesn't have much of a rotation component in its orbit. And the radial action similarly quantifies how radial the stellar orbit is. And also for the stars at the same energy level, the larger JR indicates that the star is on more radial orbit, and so on. Now, I'd like to draw your attention for these energy levels, which I indicated with two red lines. We can see the distribution, for example, in J5 or in JI is quite different between this metal-rich and metal-poor halo. This is so what it means here is for the metal-rich stars, metal-rich halo stars, it has a higher JR, which means they tend to have more radial orbits, and as a consequence of that, you kind of see them possessing a less J5 for the same star, so giving us kind of pointy tip distribution. And this is this effect is due to the selection function, because for the stars, in order to enter our the volume of our data, it needs to be on a radial orbit for the stars at the higher energy or the lower energy. Because if they're on a circular orbit, they will just be orbiting around at a larger radius, so which we cannot really detect. So this kind of indicates that we do have more radial stars for this particular halo stars compared to the metal-poor stars, which we don't really see like such thing, while the selection function is like practically similar. So this already tells us that there are some morphological difference between relatively metal-rich part of the halo and the relatively metal-poor part of the halo. And the interesting thing is this kind of a morphological transition doesn't seem to be a smooth transition. It seems to be some sort of like a jump. So the radial anisotropy, we can see there's a like sudden transition between this like older and younger population, and the.
So this plot is just for halo stars.
Mm-hmm.
I mean, how did you remove these stars, or what about?
So
disks?
Yeah. So in this case, it was a rather simple removal. So I think for this study, so this is from a different study. For this study, when you look at these like 3-5 versus metallicity, you kind of see a very clear separation between the like a thin disk and then a bit of an evolution of a thick disk. and then you kind of see a more sparse cluster of stars, which has a like a which sitting at like J5 here, V5 here, and then metallicity here, V5 around like 0. So from the very simple like clustering, that you kind of get a like good enough selections for these halo stars. So it should have like bit of a velocity bias around the like higher metallicity range, where you kind of start overlapping between the thick disk and the halo, but primarily this effect shouldn't be a big one. And if there is, it should be quite easy to pick up, because like thick disk stars, we kind of expect them to have a very specific V5 or other chemical. So the one interesting thing is this kind of transition seems to be a very a sudden change, which kind of indicates that maybe it probably is not some smooth evolution of from the metal poor halo to the metal richer halo, but it seems to be there like two just different components from the two different formation scenario. And this actually led to one of the very interesting discovery from the Gaia, that which we call the GSE, or the Gaia sausage, or Enceladus, because like sausage, because you probably want to refer to this paper that shows that when you plot the velocity ellipsoid, it kind of looks like it gives a very elongated shaped sausage. And later it came with the more beautiful name Enceladus, so now we call it GSE. So yeah, for this metal rich halo component, which seems to be dominated with the very radially orbiting stars. But for the metal poor star, it seems to be more isotropic, which probably indicates more of a like a random low mass accretion from all the direction at the earlier time. So it gives like almost like net zero rotation, and yeah, practically isotropic. Now, so this metal-rich halo, which is dominated by this debris from the GSE merger, also shows a very distinct chemical signature. Here we can see the halo stars here, these bits, which is most identifiable from their lower metallicity and the high orbital eccentricity, which is color-coded as red, compared to this like thick disk and then thin disk stars. So the halo stars are showing quite a unique alpha abundances pattern. Now, this decreasing trend of alpha ratio among the metallicity range is often called the alpha Ni, which is visible when the supernova type 1a becomes the dominant ISM polluter. On the right panel, we are showing the magnesium over Fe. So the magnesium is one of the typical alpha elements, versus the metallicity for the Milky Way stars in gray, and the other stars from the other satellite galaxies that we still see in current days. And we can see that the lower mass system tend to have alpha Ni transition at lower metallicity, and this is again because of the difference in the star formation rate between these galaxies at that the higher mass the higher the mass of the progenitor galaxy, the higher the star formation rate. So the metallicity growth is faster within this fixed time period. So now we can see these the halo stars in the Milky Way are showing an early alpha Ni transition, and this in fact is very similar to what is expected from the stars born in the dwarf galaxies. So that's like smaller mass system. And it, of course, could be the case that the halo was just formed in situ and the star formation rate was just low at that region of the galaxy, but it is actually very unlikely to have sufficient star formation at all in the current halo region, unless there are some specific like external input or energy and resources. Now, there are some clues from the simulation for this GSE merger. So this is a plot from the Fatah et al. 2019, and there are many more simulations since then. And so this is showing the dark matter accretion history of Auriga galaxies, and that are normalized to the present day halo virial mass. So on the left, it is showing the velocity anisotropy and the halo mass contribution. And in the middle, is showing the accretion history for the galaxies, which is in red. It illustrates the case that the galaxies with the very radially biased stellar halo components, which are located here in the top right corner, and the blue lines corresponds to the accretion history of the rest of the galaxies from the simulation. Now here we can see that for the case of the Milky Way halo, isn't too rare. I mean, well, it's a very small number statistic, but it's not like 1 out of something case. It is about like 1/3. So it's probably not like super rare, and also these cases tend to have a very rapid growth in mass, meaning that they experience some major merger event at relatively early time, and then since then it has a relatively quiet accretion history. Now on the right panel, it is showing the progenitor mass versus merger time for those galaxies like selected before. And although it is quite a broad distribution and also a very small number statistic, we can actually see it gives an estimate for the progenitor mass around like 10 to the 9.5, 10 to the 10 is solar mass, with the merger time around 9 to 10 Gaia years ago. This estimate is in line with other estimates from like different methods, such as like stellar population studies or global cluster count studies, and it is also in line with the fact that the current thin disk we see in the galaxy and its age distribution, it actually requires a rather quiet accretion history since some last major merger to give it enough time to build a thin disk that we see in current day. So a brief summary so far for the JAC. So one of the most interesting findings from Gaia is probably that the major merger event occurred in the Milky Way about 10 Gaia years ago. This galactic merger, GSE, have largely contributed to the Milky Way's metal-rich halo components, and there are ex situ global clusters that was brought into the Milky Way during this merger, originated from the GSE. The David Massari here is a super expert in this. Ever since the Gaia DR2 data release, there are many studies that started to make use of the dynamics and chemistry of the stars or global clusters individually. So we can actually use either of the dynamical or chemical information only, which also, it actually does have a benefit of using the other information for the cross confirmation of the analysis, either based on their dynamics or chemistry. But still, the dynamics or chemistry usually only shows like one side of the story, or sometimes it can even confuse us. Like, for example, there are stars with very high orbital eccentricity, making it very much look like ex situ halo stars, purely from the dynamical point of view. But yet, when you look into their chemical abundances, they are very much like Milky Way thick disk stars, just undistinguishable. So there are complications in stars chemistry and dynamics. So perhaps it would be useful to include like both chemical and dynamical information from the beginning, and see if we can trace some building blocks of the galaxy simultaneously. Now here we can use multi-dimensional clustering algorithms such as mixture modeling for our analysis. In this case, so this is an unsupervised probabilistic modeling for unlabeled data, which is a suitable case for us. So the basic idea is quite simple, that we assume that the overall data distribution as a sum of a number of model distribution, for example, like Gaussians, with unknown parameters. And then the optimal solution, the optimal model with the maximum likelihood, can be searched. Like here, what we need to remember is that this model distribution, for example, Gaussians, it may not be, most certainly not be is a good representation for the actual distribution of the real components in our data. So although the clustering algorithm can find some noticeable groups in the data, there are no guarantee that these groups are always like physically meaningful, nor are indeed different entities. But still, this gives us a very interesting opportunity to actually disentangle any chemodynamical trend in our hyperdimensional data set. Now, let's have a look on some example of multidimensional chemodynamical study for the Milky Way's eccentric stars. So stars on a like very eccentric orbits. So in this case, it's a cross-match data set from the Gaia and an APOGEE, and we can obtain a number of useful dynamical information such as orbital energy and eccentricity. And together with this, we can make use of various chemical traces such as alpha elements or aluminium, manganese, cerium, which are the traces of different nucleosynthetic process. So we use the Gaussian mixture model on this like multidimensional space to identify if there's any like hemodynamical groups in our data set. And we use a BIC test to figure out the optimal number of the components and to avoid the potential overfitting. We also performed a similar study with a different combination of data set. In this case, we use a Gaia and GALAH, which also provides a more chemical abundances. So this is the result from the Gaia GALAH dataset, which we actually got an agreeing result to the case from the Gaia APOGEE. So you kind of can see the main component detected ended up giving a rather similar result. So it kind of gives a bit of a more credence on the result that we got from the APOGEE's case. Now, the GALAH does provide more chemical abundances than APOGEE, but their measurement uncertainty is considerably larger than APOGEE. Yet, GALAH, we could include more than one tracer elements for each elemental types. But today, we will focus on APOGEE result, which anyway is telling the same story. Now we can see there are like 5 main components detected from this GMM study, like green, yellow, red, blue, and magenta components. All the dots are the Milky Way stars with the high orbital eccentricity, which we applied our GMM Gaussian mixture model analysis to study the composition of halo or the halo-like stars in the Milky Way. The background grayscale density map is all stars from the Gaia APOGEE cross-match. So you can see like thick disk and the thin disk distribution quite clearly from there. Now, some components correspond to the already known structures that we briefly covered already, such as GSE. And we could cross-check the chemical and dynamical properties of each identified component with the known ones. Here, actually, there's quite an interesting point that the GSE population marked with the yellow and the green, meant to put an arrow there, but yeah, yellow and green, is identified as 2 separate Gaussian components. And as I mentioned before, there's no reason for the actual physical trend to follow our model distribution, in this case, like Gaussian. So if a population is showing some distribution that deviates a lot from some single Gaussian distribution, then it can be separated into multiple groups for rather obvious reason. And in this case, because the GSE is very prominent entity in our halo sample, and because it is detectable across a wide range of metallicity, we are actually capturing the both alpha abundances pattern trend for the GSE. One is like before and after the supernova type 1a transition. So the yellow component here, the lower metallicity GSE is capturing the earlier subpopulation of the GSE before the supernova type 1a onset, and the green components is capturing the higher metallicity GSE, which is a relatively younger part of this entire GSE population, which after the supernova type 1a dominance. So this also can be checked from the aluminum over Fe trend here. Yeah, so the yellow and green. We are seeing some very mild increasing trend from these yellow components and the decreasing path for the green, which is altered. And as a result of this like supernova type 1a onset, like kicking in. So we also can see that the overall level of the aluminium for this entire GSE population is much lower. Is much lower than the other populations, which is like dominantly the Milky Way in situ population. And so for the GSE population, seems it never managed to achieve a high aluminium over Fe ratio due to its rather limited star formation and self-enriching history compared to our Milky Way, which was a lot larger entity when the merger happened. So this again kind of confirms the GSE's ex situ natures and as a past merged and disrupted dwarf satellite galaxy. Now let's briefly talk about the other population in this eccentric sample. The first is the magenta population here, which is also a known population called a splash. So this population was quite an enigma for us because its orbit is very much like halo components, like 0.9, like 0.8, 0.9 eccentricity, just like many other halo stars, but its chemistry is just like a typical thick disk stars. So we can see like very high level of alpha and also very high level of aluminum abundances for these splash components compared to the like other population like a GSE, even at the same metallicity range. Well, they have a like small overlap, but still. So this splash is quite an interesting component for our galaxy that it seems is a protodisk population prior to the GSE merger, which then got dynamically splashed as a consequence of this merger event. And now they have this very halo-like orbit, while it has a very disk-like chemistry because it was actually born in the Milky Way. We also can see that this splash has lower orbital energy than the majority of the GSE debris, which also makes sense. And the splash stars have an age older than the GSE merger time, which is around 10 Gaia years ago, we think. So in the second panel, it is showing these row normalized density map for these Milky Way stars and its metallicity and V-phi. And we can see around like minus 0.5 here. So on the like this sketch here, we can kind of see this thick disk trend is actually skewed all the way down to like V-phi equals 0. So it's kind of showing like very like low orbital trend. So on the far right, so we selected minus any stars above like minus 0.7, so just roughly to select these like in situ like stars, and you do see like a rather rapid, very like clear like truncation around this this time. Now, another interesting halo-like yet an in situ component is the red component here. Okay. It's called Aurora, so it's another known component. This is a metal poorer population than the splash and is showing a very interesting alpha and aluminum pattern. So this appears to be a very ancient in situ population covering the very early chaotic like pre-disk evolution time to a spin-off phase of the Milky Way. Now here the first panel is showing this magnesium of Fe versus metallicity, and the author applied, which is not me, applied a very crude cut to just roughly select these accretive stars, high alpha in situ stars and the low alpha in situ stars. And when you just, even from this like rather crude selection, if you just start analyzing, like having a look on them on aluminum space, you kind of see like very different trend already, which is also the trend kind of we picked up from this GMM study, which kind of cross confirms that this trend actually exists in the data. Now on the middle panel, which is capturing this aurora population, we can see like very rapidly rising aluminum sequence. And this trend is what we picked up, again, what we saw from the GMM analysis. And And this is a phase that we think that the Milky Way was going through a very rapid star formation and very rapid, like very efficient self-enriching. And we can see this enrichment is extended more than an order of magnitude, which is probably very unlikely for the case of the dwarf satellites, like even for some large dwarf satellite, we think, such as like GSE, but probably was only achievable for some Milky Way sized galaxy progenitor. So they also show like lower orbital energy than all these accreted stars, for example, like GSE populations. Now, they show like nearly isotropic velocity distribution with very mild net rotation, and it also indicating that this pre-disk evolution. So it also indicates that this probably is likely like this pre-Milky Way disk evolution phase. Now here again, so here we can see like this is the mean V5 at each metallic spin, and so this is like top 95% quantile, and then the lower 5% quantile, and you can see is a very like broadly spreaded in terms of like a V5, which, as you see that this increasing trend with a spin-up trend, and which so which is capturing this like a spin-off phase of the Milky Way. And so we see a rather similar trend from the like a number of simulations, like Milky Way sized galaxy formation simulation, that is there's like a period of this like chaotic like pre-disk evolution when the gases are accreted along these cold narrow filaments from here and there, and when the stars are born in rather irregular configuration, which is resulting this very broad distribution in V5, which is followed by this like subsequent disk formation. So, and the latter actually signals the formation of the stable like hard gaseous halo around the Milky Way progenitor, which changes the mode of the gas accretion and allows this development of the more coherently rotating disk. Now, the last main component I'd like to mention today is the blue component here called EOS. Here, and EOS is another very enigmatic population here that chemically it looks rather similar to the thin disk, but it is very metal poor for an in situ thin disk, and their population includes the stars with the higher eccentricity. Now, is relatively high metallicity and high aluminum abundances. They kind of indicate the EOS to be a relatively young population among these populations, and to be an in situ population. Now, our interpretation for EOS is a population originated from the gas that is polluted by the GSE, which evolved to resemble the outer thin disk of the Milky Way. So similar to Aurora, EOS is showing a considerable level of enrichment in aluminum abundances, not as rapid as Aurora case, but clearly different from some like GSE or other low mass dwarf galaxies. So an interesting point here is that there has been many theories on the outer disk formation mechanism, like for example from Haywood et al. 2019, which is the sketch that I borrowed from. And this process kind of involves the leftover gas from the earlier thick disk formation and some other gases acquired from some outer radii of the Milky Way, which causes the stars to have like low evolved alpha element, yet relatively lower metallicity than the end of this thick disk sequence, as this acquired gas is relatively pristine and could reset the metallicity back a bit up to a certain degree. And naturally, the degree of this dilution would depend on the galactic radii, that the further away from the galactic center, the thick disk gas portion will be lower, so the more dilution, so lower metallicity. But of course, this outer disk hasn't really been found at low metallicity range, like below minus 0.7 or so until now. And also this the proposed source of this like dilating gas, there are like many variety between different theory and different studies. A very interesting case was actually found from a simulation that the Wintergarten simulation team reported a case that a major merger actually can trigger some sufficient outer disk star formation on its approach. If there is a gas on the right alignment to this merger track. But in this case, the Wintergarten actually required another gas channel, a separate filament from the main one that fuels the outer region of the host galaxy. So the gas used for this outer disk formation can actually have a different chemical, for example, like alpha or metallicity composition compared to these inner disk stars. So although it does require some very specific settings, like some additional gas filaments and very like right alignment with the main galaxy and also to the merger's orbital path, the result is quite remarkable that actually they managed to produce that the outer disk stars can have a low alpha abundances, and also with the low metallicity compared to the stars that were formed at the same age. So they seem to resemble this outer disk or this EOS population that we see here like quite well. But here in our case, we suggest that instead of the gas acquired from some additional gas filament, we are suggesting that the gas that form this outer metal pore disk, it could be sourced by this gas from the GSE that were brought into the Milky Way during this its very own merger process, and of course the in situ gas mixed with the in situ gas left after the thick disk formation. So apart from the fact that this requires the like less fine tuning, we also see some interesting chemical trend of EOS. That the EOS chemistry seems to be relatively similar to the GSE's at EOS's low metallicity end, which is comparable to the higher metallicity end of the GSE, and this is also in line with the general idea of the different degree of gas dilution between the in situ and the GSE originated gas at the different location and different stage. So more contribution from the GSE gas will naturally result more similar chemical abundances at that metallicity level, and this gas after the thick disk formation and the gas contributed from the GSE merger will gradually become more mixed and eventually evolves into more typical disk at higher metallicity. And as the gas get more mixed and also get dynamically aligned to the galactic plane, this like a non-disky orbit of the EOS at the lower metallicity also we expect it to become more disky as we move to the later stage, the higher metallicity. So a quick recap for today. So there are major merger events in the Milky Way which have modified the galaxy and created a number of galactic components. And there's a merger contributed heavily. There's a merger contributed. This merger heavily contributed to the Milky Way's metal-rich halo, and also dynamically splashed a portion of this protodisk, and also polluted the gas for the outer disk population. And we also found a pre-disk like in situ population formed during the rapid star formation period of the early stage of the Milky Way. This is all I've prepared for today. Thank you very much for listening.
Thank you. I forgot to announce that for the students, the speaker has agreed to stay after we all leave, and you can meet with him and you can ask him any questions you wish. And discuss more background to this subject. Does anybody have any questions?
So about your Gaussian mixture model in which you are trying to separate the different components. It's not clear to me what are the actual integrals of motion that you are using. I mean, it looks like in your plot you have energy, but then you were mentioning.
Yeah. In this case, I didn't include any like action variables for these cases, because I wanted to keep it rather simple, or because I wanted to have some component from dynamical side and some component from the chemical side, and the actions, the total sum of the action kind of reflects the energy. So I only use the energy as a kind of representative value for that. But you're right, in this particular case, the action variable itself hasn't been included.
So only the, not even the vertical component of the angular component.
Yeah, because
using only the energy.
And there is actually a reason for it, because in this case we were focusing on this like very halo or halo-like stars, which we applied kind of like a eccentricity cut, which anyway bias this kind of a angular momentum distribution or even like action distribution. So it is kind of biased to use angular momentum for like some detailed interval of motion information. So we just use the energy as a total sum, which still remains relatively unbiased for even population.
So just to be clear on this point, so your hyperspace where you apply the distribution model, how many dimensional that's?
I actually forgot, but it depending for the APOGEE. Sorry,
you have one dynamical dimension that is energy, because you have already
because we kind of like took a like easy way to focus into the
and then what are the dimension on chemical side?
So like metallicity, like aluminum as a representative one for the old set, and then actually we can actually back a bit. Like cerium as a like R process element, and a magnesium, manganese, and like.
So all of these are dimensional of the hyperspace.
Yeah.
It's a chemical hyperspace.
It is very like it's just a bit of like energy. And today I didn't really mention about this like energy like differences, but like energy we kind of use as an indicator for like a okay, like we kind of see this like aurora supposed to be a very early stage of the Milky Way formation. It is just odd to see them having like really high energy orbital energy, for example, and the GSE supposedly this accreted one. It'd be odd to see like say like splash population which gets some energy transferred from the GSE ended up having like higher energy. So it's more like a quantitative comparison. And of course that our main goal is eventually get rid of this eccentricity cut, so we can actually make use of a real more dynamical information. But then it's a hyperdimensional problem, and then you start having like too many like interloopers from disk, etc., which just becomes a rather a messy business. So it's all to do with the computational power that we can make use of.
Yes, thanks. Very nice talk. So I have 2 questions, maybe more, but we'll have time for that. So one is, where does Sequoia would end up in this eccentric component? Does it end up in the GSE component, or is it out of the?
So in this case, we actually applied even higher eccentricity cut than what we would normally see if this like Sequoia, because in this case it was like 0.85. So most of the Sequoia components wouldn't actually make a cut, and even if it makes a cut, because it's not a, like it has a like distribution on eccentricity. The GSE is just a 2 dominated features that it just like overshadows everything. Like for example, like not just even for Sequoia, like say like Arjuna or like Iltoi or like Wukong, or like if you believe in like any of them, like but all these like proposed one, it's just very difficult to actually spot when you have a giant like GSE overpainted oil. So the GSE I think is kind of like a blessing for us, because it really tells us so much about how the Milky Way gets kind of built up. But at the same time, it also shadows like so many finer details underneath. Yeah.
But so in your overall interpretation, these other small substructures still exist. They're not part of GSE. They are independent ones, smaller, that are overshadowed by this.
Yeah, because I think it is quite so the GSE say like for the stellar ratio like 1 to 10, dark matter ratio say like 1 to even 5 each. But then Milky Way, I mean, had to grow up to like current state, and so which I think naturally involves some sort of like a smaller subsystem, and that's also in line of this hierarchical like evolution. And also, so because how I kind of like thought the sequoia was sequoia as a kind of like a subsystem of the GSC, like LMC and the SMC, and then it's many other minions, you know, like we know like how many the large Magellan cloud system has like smaller like fainter dwarfs, right? Like there's so many, and then GSC was supposed to be even more impactful entity even back at that time. So I think it is quite odd to not see any like separate things, but probably like belongs to its kingdom, its regime, but probably not necessarily integrated into the like same body. But that's how I kind of portray it.
Okay. Yes, that's right. And then the other question is on EOS. I must say I'm the structure I'm least familiar with.
Yeah, yeah.
But if I understand correctly, you would expect EOS stars to be all younger than Gaia Enceladus stars, right? Assuming Gaia Enceladus stopped star formation when it came in.
Yeah, so we kind of think so because this EOS case, they're chemically very much like low alpha disk, and we kind of know like low alpha disk only could have been formed like after all this like mergers and everything, and there has been like many proposals and many like suggestions for how this like especially for the outer disk got like formed, because inner radius like there are like many like resonances that can like easily induce disk formation. Like the major work is from like Haywood et al. Like kind of like try to explain like yes, there could be some mixture of like a gas